In this video, I am going to talk about processor allocation algorithms. A distributed system consists of multiple processes. These may be organized as a collection of personal workstations, a public processor pool, or some hybrid form. In all cases, some algorithm is needed for deciding which process should be run on which machine. For the workstation model, the question is when to run a process locally and when to look for an ideal workstation. For the process pool model, a decision must be made for every new process. So in this section, we will learn the algorithms used to determine which process assigned to which processor. Uh, a large number of processor allocation algorithms have been proposed over the years. We will look at some of the key choices involved in this algorithm and point out the various important points. The major decisions the designer must make can be summed up in 5 different issues. Number one, deterministic versus heuristic algorithm, centralized versus distributed algorithms, optimal versus suboptimal algorithms, local versus global algorithms, sender initiated versus receiver initiated algorithm. Decision issues for processor allocation algorithm. Deterministic algorithms are appropriate when everything about process behavior is known in advance. At the other extreme are systems where the load is completely unpredictable. Processor allocation in such a systems cannot be done in deterministic mathematical way, but of necessity uses ad hoc techniques called heuristic. The second design issue is centralized versus distributed. Collecting all the information in one place allows a better decision to be made, but is less robust and can put a heavy load to the central machine. Decentralized algorithms are usually preferable, but some centralized algorithms have been proposed for lack of suitable decentralized alternatives. Third issue is related to the first two. Are we trying to find the best allocation or merely an acceptable one? It involves collecting more information and processing it more thoroughly. In practice, most actual distributed systems settle for heuristic, distributed, suboptimal solution because it is hard to attain optimal one. The fourth issue relates to what is often called transfer policy. When a process is about to be created, a decision has to be made whether or not it can be run on the machine where it is being generated. If that machine is too busy, the new process must be transferred somewhere else. The choice here is whether or not to base the transfer decision entirely on local information. If the machine's load is below some threshold, keep the new process, otherwise try to get rid of it. The fifth issue deals with location policy. Once the transfer policy has decided to get rid of a process, the location policy has to figure out where to send it. Location policy cannot be local. It needs more information about the load elsewhere to make an intelligent decision. This information can be disseminated in two ways. However, in one method, the senders start the information exchange. In another, it is the receivers that take initiative. Processor allocation algorithm. A simple example, the figure is shown on the screen. Here, an overloaded machine sends out requests for help to other machines in hopes of offloading its new process or on some other machine. The sender takes the initiative in the loading more CPU cycles in this example. In contrast, the B diagram on the screen, a machine that is idle or underloaded announces to other machine that it has little to do and is prepared to take an extra work. Its goal is to locate a machine that is willing to give it some work to do. Implementation issues for processor allocation algorithms. Whether it is overloaded or underloaded. To start with, virtually all the algorithms assume that machines know their own load. So they can tell if they are underloaded or overloaded and can tell other machines about their state. Measuring load is not as simple as it first appears. One approach is simply to count the number of processes on each machine and use the number as a load. However, as we have pointed out before, Even on an ideal system, there may be many processes running, including mail and news daemons, window managers, and other processes. Thus, a process count says almost nothing about the current flow. The next step is to count only processes that are running or ready. After all, every running or runnable process puts some load on the machine, even if it is a background process. However, many of these daemons wake up periodically, check to see if anything interesting has happened, and if not, go back to sleep. Most put only a small load on the system. A more direct the measurement is, although it is more work to capture, is the fraction of time the CPU is busy. Clearly, a machine with a 20% CPU utilization is more heavily loaded than one with a 10% CPU utilization. Whether it is running user or daemon programs, one way to measure the CPU utilization is to set up a timer and let it interrupt the machine periodically. At each interrupt, the state of the CPU is observed. In this way, the fraction of time spent in the idle loop can be observed. Then how to deal with the overhead? A proper algorithm should take into account the CPU time, memory usage, and network bandwidth consumed by the processor allocation algorithm itself. How to calculate the complexity? If an algorithm performs a little better than others but requires much complex implementation, better use the simple one. How to deal the stability? Problems can arise if the state of the machine is not stable yet, still in the process of updating. Example, processor allocation algorithm, a graph theoretic deterministic algorithm, a centralized algorithm, a hierarchical algorithm, a sender initiated distributed heuristic algorithm, receiver initiated distributed heuristic algorithm, a bidding algorithm. The first one, graph theoretic deterministic algorithm. The system can be represented as a weighted graph, with each node being a process and each arc representing the flow of messages between two processes. Problem then reduces to finding a way to partition the graph into k disjoint subgraph subject to certain constraints. For each solution that meets the constraint, arcs that are entirely within a single subgraph represent intra-machine communication and can be ignored. Arcs that go from one subgraph to another represent network traffic. The goal is then to find the partitioning that minimizes the network traffic while meeting all the constraints. The following figure shows two ways of partitioning the same graph, yielding two different network loads. In this figure, we have partitioned the graph with the processes A, E, and G on one processor, processes B, F, and H on a second, and processes C, D, and I on the third. The total the network traffic is the sum of the arcs intersected by the dotted cut lines, or 30 units. In the V diagram on the screen, we have a different partitioning that is only 28 units of network traffic, assuming that it meets all the memory and CPU constraints. That is better choice because it requires less communication. As in the previous figure, we have partitioned the graph with the processes A, E, and G on one processor B, F, and H on a second, and process C, D, and I on the third. The total network traffic is the sum of the arcs intersected by the dotted cut lines, or 30 units. In the B part of the diagram, we have a different partitioning that is only 28 units of network traffic, assuming that it meets all the mandate memory and CPU constraints. That is a better choice because it requires less communication. A centralized algorithm. It does not require any advanced information. It is centralized in the sense that a coordinator maintains a usage table with one entry per personal workstation, initially 0. When significant events happen, messages are sent to the coordinator to update the table. Allocation decisions are based only on the table. These decisions are made when scheduling events happen, a processor is being requested, a processor has become free, or the clock has ticked. Centralized algorithm, when a process is to be created, and the machine it is created on decides that the process should be run elsewhere. It asks the usage table coordinator to allocate it a processor. If there is one available and no one else wants it, the request is granted. If no processors are free, the request is temporarily denied and a note is made of the request. When a workstation owner is running processes on the pupil's machine, it accumulates penalty point, a fixed number second as shown in the previous figure. When no requests are pending and no processes are being used, the usage table entry is moved a certain number of points closer to zero until it gets there. In this way, the score goes up and down, hence the name of the algorithm. Usage table entries can be positive, 0 or negative. A positive score indicates that the workstation is a net user of system resources, whereas a negative score means that it needs some resources. Zero score is neutral. A centralized algorithm, the heuristic used for processor allocation, when a processor becomes free, the pending request whose owner has the lowest score wins. As a consequence, a user who is occupying no processes and who has had a request pending for a long time will always beat someone who is using many processors. This property is the intention of the algorithm to allocate capacity fairly. To organize them in a logical hierarchy independent of physical structure of the network, as in micro, this approach organizes the mission like people in corporate, military, and academic, and other real-world hierarchies. Some of the machines are workers and others are managers. For each group of K workers, one manager machine is assigned the task of keeping track of who is busy and who is idle. If the system is large, there will be an unwieldy number of department heads. So some machines will function as deans, each riding head on some number of department heads. If there are many deans, they can be organized hierarchically. This hierarchy can be extended with the number of levels needed growing logarithmically with the number of workers. Since each processor need only maintain communication with the one superior and a few subordinates, the information stream is manageable. The hierarchical algorithm diagram is shown on the screen. To avoid having a single manager at the top of the tree, one can truncate the tree at the top and have a committee as the ultimate authority, as shown in this diagram. When a member of the ruling committee malfunctions, the remaining members promote someone one level down as replacement. While this scheme is not really distributed, it is feasible and in practice works well. In particular, the system is self-repairing and can survive occasional crashes of both workers and manager without any long-term effects. The hierarchical algorithm. What happens when a department head stops functioning? So the answer for this question is to promote one of the direct subordinates of the faulty manager to fill in for the boss. The choice of which can be made by the subordinate themselves, by the deceased peers, or in a more autocratic system, by the sick manager's boss. To avoid having a single manager at the top of the tree, one can truncate the tree at the top and have a committee as the ultimate authority as shown in the previous diagram. When a member of the ruling committee malfunctions, the remaining members promote someone one level down as replacement. Sender-initiated distributed heuristic algorithm. The algorithm described above are all centralized or semi-centralized, and distributed algorithms also exist. When a process is created, the machine on which it originates sends probe messages to a randomly chosen machine, asking if its load is below some threshold value. If so, the process is sender. If not, another machine is chosen for probing. Probing does not go on forever. If no suitable host is found within n probe, the algorithm terminates and the process runs on the originating machine. The sender-initiated distributed heuristic algorithm, an analytical queuing model. Using this model, it was established that the algorithm behaves well and is stable under a wide range of parameters, including different threshold values, transfer costs, and probe limits. Under conditions of heavy load, all machines will constantly send probes to other machines in a futile attempt to find one that is willing to accept more work. Few processes will be offloaded, but considerable overhead may be incurred in the attempt to do so. A receiver-initiated distributed heuristic algorithm. Whenever a process finishes, the system checks to see if it has enough work. If not, it picks some machine at random and asks it for work. If that machine has nothing to offer, a second and then a third machine is asked. If no work is found with n probe, the receiver temporarily stops asking, does any work it has queued up, and tries again when the next process finishes. If no work is available, the machine goes idle. After some fixed time interval, it begins probing again. Bidding algorithm. Another class of algorithms tries to turn the computer system into a miniature economy with the buyers and sellers of services and prices set by supply and demand. It was introduced by Ferguson and others in 1988. The key players in the economy are the processors, which must buy, say, CPU time to get their work done, and processors, which action their cycles off to the highest bidder. Each processor advertises its approximate price by putting it in a publicly readable file. This price is not guaranteed, but gives an indication of what the service is worth. Different processors may have different prices depending on the speed, memory size, presence of floating point hardware, and other features. A bidding algorithm is continued. When a process wants to start up a child process, it goes around and checks out who is currently offering the services that it needs. It then determines the set of processes whose services it can afford. From this set, it computes the best candidate, where best may mean cheapest, fastest, or best price or performance, depending on the application. It then generates a bid and sends the bid to its first choice. The bid may be higher or lower than the advertised price. Processors collect all the bids sent to them and make a choice, presumably by picking the highest one. The winners and losses are informed and the winning process is executed. The published price of the server is then updated to reflect now the new going rate.